Hi everyone! Today let's talk about session 12.2, Graphs and Level Curves. Before this class, you studied functions of the form y equals f of x in Calculus 1 and Calculus 2, right? Such a function inputs a real number and outputs a real number. And we usually say x is the independent variable and y is the dependent variable. And we may write f is a function from R to R. R denotes the real numbers, okay? We will now study multivariable functions, which input multiple numbers simultaneously and outputs real numbers. For now, to make it easy to visualize, we'll focus on the function that inputs two variables and outputs one real variable. Such a function will be of the form z equals a function of x and y. We usually say x and y are the independent variables. So here we have two independent variables. They're like the inputs. And z is the dependent variable. So z is like the output. Unless otherwise stated, x and y are assumed to be independent of one another, then we can write f is a function from R2 to R. Sorry, there's a typo here. This should be R. Okay, so domain and range of a function z equals f of xy. The domain of a function z equals f of xy is the set of all possible input pairs xy. We visualize the domain as a set of points in the xy plane. The range of f is the set of real numbers z that are assumed as the point x, y varies over the domain. A set is said to be open if it contains none of its boundary points. Closed if it contains all of its boundary points. So here in R1, real numbers, open, you can think of an open interval like this, right? It does not contain the boundary points. So let's say if this is 1, 2, then this is the open interval 1, 2. So it is open. Well, closed means you include the endpoints, right? So we have, so usually when we not include the endpoint, we use open circle. When we want to include the endpoint, we'll use a solid circle. Okay, and we use bracket to denote. So this interval is closed. How about in R2? Well, in R2, an open interval looks like this. We use dashed line to denote the boundary is not included, and we use solid line to denote the boundary is included. So this guy is open, and then this guy is closed. So far, so good, everybody? Okay, look at the example. Find and sketch the domain of each function. Is the domain open, closed, both, or neither? Okay, so do you know there are some sets are both open and closed? So both, example for both open and closed, it could be the empty set, or it could be the whole space. Let's say if we're talking about xy plane, then R2 is both open and closed. Okay, so neither, you can think of an example that it has dashed line and then solid line somewhere. So here it contains some of the boundary, but not all of the boundaries, because it has some boundaries, so it's not open. Because it does not contain all the boundary points, it's not closed. So this is neither. So far, so good, everybody? So we can have the set open or closed or both or neither. All right. So let's look at the following functions. Do you still remember if we want to find a domain, what do we want to look at? So here are the three main type of functions with restricted domain. Okay, first, We have square root function, and what do we need? We need the things inside the square root to be greater or equal 0. And then second, we have fraction. What do we need? We need the denominator to be not 0. And then we have natural log. And what do we need? We need the things inside natural log to be positive. And other functions, for example, tangent, cotangent, secant, cosecant. We also have restricted domain. Okay, so keep those in mind. I can put it here. Tangent, cotangent, secant, cosecant. Okay. So the vertical asymptotes are the points that are not in the domain. Okay, let's continue. A. Okay, so do we have square roots? Yes. Then what do we need? We need the things inside the square roots to be greater or equal 0. So let's move the x squared and y squared to the right hand side. Then we have x squared plus y squared. Right? It's like you add x squared on both sides and you add y squared on both sides. Well, this is the same as x squared plus y squared less than equal to 4. Do you know what that is? You know when it's equal to 4? So when it's equal to 4, this is a circle centered at the origin with the radius is it 4? No, square root of 4, which is 2. Okay? So that is a circle. And because here, you see this equal sign? That's why we put solid line. We don't put dashed line. If this is less than 4, then we put dashed line. Because it's less than equal, so we know the distance from the origin to the point less than equal, so it's inside the circle. So this is the domain, okay? And if we want to use a set to denote, then the domain is the set of points x, y such that x squared plus y squared less than equal to 4. Is this closed? Does it contain all of the boundary points? Yes, it is. So this guy is closed. So far, so good, everybody. Let's continue to look at example part B. Okay, do we have square root? Nope. Do we have fraction? No. Do we have natural log? Yes. Then what do we need? We need the things inside the natural log to be positive, right? And you can see y is degree 1, x is degree 2, so it's a parabola, right? It's a parabola, so we can express y, move the x on the other terms on the right hand side, because we can think of y is like a function of x. Then we have minus x squared plus 1. So far, so good, everybody? Alright, what is this guy? You know, think about what is y equals minus x squared plus 1. Well, this is a parabola, and because this is negative, it opens down, right? And because this is 1, it passed through the point 0, 1. And it opens down. Okay, we know it looks like this, but look at it carefully. Do we have equal here? No. Then what does that mean? We put dash line, right? And y is greater or equal. So greater or equal means it's bigger. So, okay, so is it on top of the parabola or below the parabola? Bigger number is on top, right? It's greater than, so we pick this region. So this set is the points x, y such that y is greater than minus x squared plus 1. Is this guy open or closed? You see, it does not contain the boundary points. Okay, it does not contain any of the boundary points, so this guy is open. Alright. So sometimes you might have several conditions, so you might need to combine them. Okay. For example, I can just make it up. Oh, I don't have enough space here. But I can just simply make up a problem. Let's say C, f of x, y is square root of 4 minus x squared minus y squared. This is our part A, plus ln of y plus x squared minus 1. Well, this is just combine the A and B together. So when you draw the picture, what happened? So when you draw the picture, you have the 2 you want to include, and there's a 1 there. Okay, so this is 1, this is 2, and then you want to then this is the portion. Can you see? Those shaded area is the portion. You can see the top we have include a boundary, but this guy does not include a boundary. So this is neither open nor closed. Okay, so if you want to describe the set, well, you can just put all the conditions right here. So less than equal to 4 and you use and because we have to satisfy both conditions. Okay, very good. Let's continue. Graph of a function z equals f of xy. The graph of a function f of xy is the set of all points x, y, z for which z equals a function of xy. Each input variable is assigned a coordinate axis in the space. The output variable is assigned its own coordinate axis. Usually we draw the z axis is the output variable, okay? So we draw that's the vertical axis in the space. So in general, we visualize such graph as a surface in the space. We know y equals fx is a curve, then z equals f of xy is a surface. Okay, you might ask, oh, how about if we have more and more variable? We say those are hypersurface. Okay. Oh, typo. Hypersurface. Okay, so let's look at the following example. Sketch the graph of each function. Okay, so let's look at the first one. So we draw x, y, z. So z equals x squared plus y squared. Okay, when z equals to 0, what happened? Well, x squared plus y squared is 0. Well, that's the origin, right? And when z equals here, x squared plus y squared equals 0, it's just the points, the origin, right? And think about it, if when z equals 1, x squared plus y squared equals to 1, what do we get? We get a circle, right? So on the plane z equals 1, we get a circle with radius 1. So and then when z equals 2, we also get a circle, but the radius is like square root of 2. Okay, so that's why we will have a paraboloid. Can you imagine, everybody? Yes, so this is a paraboloid. Okay, continue. Next, oh, what happened if we have a square root outside? Well, what's this guy? This guy z is square root of x squared plus y squared. First of all, we know the z is greater or equal to 0. So it's always on top of the xy plane or in the xy plane. Okay, and if we square both sides, we get z squared equals x squared plus y squared. What is this? Okay, so here you can see when z is 0, we get x squared plus y squared is 0. So it also passed through the origin, right? And furthermore, if you plug in x equals 0, you get z squared equals y squared. So z equals plus or minus y. So they are lines. Okay, they're lines on the YZ plane. So x, y, z. Okay, so they're lines on the YZ plane. But you cannot go through the xy plane because z is greater or equal to 0. Okay, so there we have two rays. It's not lines, it's the rays. Okay, and also if y equal to 0, we get z squared equals x squared. So z equals plus or minus x. So this is also this is on the xz plane, right? And there are also lines. Okay, so we actually get a cone in this case. So far, so good, everybody. Let's continue. Alright, so z equals 4 minus x squared minus y squared. Let's square both sides. Z squared equals 4 minus x squared minus y squared. Let's move the x squared and y squared on the left. Ooh, what is this guy? This is a sphere. Center at the origin with radius 2, right? Square root of 4 is 2. So how do we draw it? Like that. Let me see. So, okay, first draw this and draw this. Okay, that's the sphere. Yeah, sometimes, yeah, practice drawing pictures. Cal 3 is like an art class. Okay. Oh, you see, this is not B, it should be D. So math professors cannot count. Okay, so what is this guy? Z equals 3x minus 2y. Okay, so what is this? You see, this is a linear equation in all of the three variables. So we know this is a plane. Okay, if it's a plane, we have x, y, z. And we know 3 points can fix a plane, right? Let's plug 3 points. Okay, we can plug in. Let's see, if x is 1 and y is 0, then z is 3 minus 0, 3. Okay, we can plug in x is 0, y is 1, then we get negative 2. Okay, so let's see, 1, 0, then we have 3 here. 0 minus 1, we have negative 2 here. Okay, one more point. How about 1, 1? So 1, 1, then 3 minus 2 is 1. Oh, so 1, 1 is 2. Okay, so we have, so it's hard to draw a plane because a plane has no boundary, but just imagine this is a plane that contains those 3 points. Okay, we know 2 points can fix a line, then 3 points can fix a plane. Okay, so 2 points fix a line, 3 points can fix a plane. And we did some example before, right? If we have 3 points, then let's say ABC, then we can use the vector AB and AC to construct the normal vector. That's the cross product, right? Once we know the normal vector and we know 1 point on the plane, then we can write down the plane equation. Okay, so far so good, everybody. How about let's use GeoGebra to plot these, okay? So let's check our where's my GeoGebra? Okay, let me open it. So let's plot those curves in our GeoGebra software to see whether we draw the a good graph. Okay, so the first one, if you just type x squared plus y squared, they already assume is a function of xy equals x squared plus y squared. So you see, we get a paraboloid. And then the next one, we have square root. Oh, how do we draw square roots? Okay, yes, square roots. Oh, they don't need the line. Okay, and here we want to put inside x squared plus y squared. Oh, you see? This is a cone. And how about the next one? Okay. Next one is square root. Enter. And then 4 minus x squared minus y squared. You see? Oh, I realized we make a mistake. It's not the whole sphere. It's only the upper half. Okay, we remember it for the cone, but I forgot for part C. The square root is only greater equals 0. See, let me use a different color because that is my mistake. Okay. So I recommend you when you see a mistake, and here, just draw the upper one. Don't draw the lower one. Okay. So only draw the upper. Okay. So the upper sphere, not the whole sphere. So be careful with that. When you see a mistake, don't just erase it. Mark it down. Okay. With minus. Next time, be careful. Don't make the mistake again. Okay, continue. Next one is a plane, so 3x minus 2y. Okay, so this is a plane, right? And don't forget, the red axis is the x, the green one is the y, and the z is the blue. Okay, so you can see this is a plane. Looks like that. And what we have, kind of like that, but you know, like plane, the plane has no boundary, so we can use rectangle to indicate this is a plane. Okay, so I hope when you do your homework, you can also plot after you draw it, plot the function in the GeoGebra software to verify your drawing. Okay. Sometimes maybe we can find some mistake. Alright, so let's continue in video part B. See you soon!